Physics Lab 4, Oscillations. This lab's purpose is to study the motion of a spring mass system of a mass oscillating in an arc in order to determine whether or not the model follows the energy principle. In order to accomplish this goal, we will use the Tracker software program to track observed position, and a computational model in GlowScript will be used to predict and graph the changes in energy and motion of the object. For a quick preview of results, the energy principle is demonstrated, shown by the fact that the system's total energy remains constant at 0. So the fundamental physics principles explored in this lab are Newton's second law and the energy principle. So Newton's second law tells us that the change in the system's momentum is proportional to the net force applied, and from this we will get these equations down below. Next, with the energy principle, it states that the change in energy of the system is equal to the sum of the work done by the surroundings plus thermal energy exchanged with the surroundings. And so in this lab, our system is the mass, spring, and earth, and the surroundings are going to be nothing, as we are going to say that this system is isolated. And then finally, here are some formulas we'll use, including the position update, velocity update, kinetic energy, gravitational potential energy, and spring potential. So now here we have the video used in the Tracker software. And so from this we get these two graphs of the position versus time for both x and y, and our initial conditions. The mass of the object is 0.402 kilograms, the initial position is listed here, the initial velocity is 0, and the length of the spring is 0.7 meters. So, first off, we need to find the period of oscillation, which is just the time it takes for the object to complete a full cycle there and back. To do this, I used the graph data and took the average of the first 3 periods, which came out to 1.523 seconds. Next, after solving for the period, we have enough information to solve for the spring stiffness, which was 6.842 newtons per meter. Finally, given all this information, we are able to manipulate this equation to find the relaxed length of the spring, which comes out to 0.1236 meters. So now for the GlowScript model, our first step is to input the initial conditions, including the mass of the object, initial position, initial velocity, spring constant, and relaxed length. Next, we add the spring length and direction, followed by the formulas and for the system energies. Finally, we are focused on the while loop. Here we are iterating each step and calculating the change in energy. To do this, we put the gravitational, spring, and net forces. These values allow us to find the velocity and position of the mass. From this, we can find the kinetic and potential energies of the system, which will give us the change in energy at each point. So here on the right, we have graphs of the observed versus predicted x and y positions. The more time goes on, the more the observed differs from the expected values. This difference could be caused by human error, as I had to pick by hand what looked like the center at each time frame, as well as the fact that in reality, the system was not fully isolated, so forces like drag from air resistance were likely acting upon the system. So is the energy principle satisfied? Yes, the energy principle is satisfied. As the system is isolated with no external forces acting upon it, the change in energy is equal to 0. As shown in the graph, the types of energy in the system change, but the total change in energy of the system is constantly 0. So finally, we can find the oscillation periods in both the x and y direction by taking the average of the first 3 periods from each graph. In comparing them, we see that the periods are different based on which direction you calculate it from. This will affect dependent variables, such as spring constant.